This is AP Calculus 8-9, volume with disk method revolving around the x or y axis. We're going to have some function, and I'm just going to name this function f of x. And let's say this f of x has a curve, and they're going to say, find the region bounded by the function and the lines, whatever they might be, that revolve around a specific axis. And they could say that it revolves around the x-axis. They could say it revolves around the y-axis. They could say that it revolves around any vertical or horizontal line that they wish. So we're going to start out simple and move into the more difficult problems. And in this section, this is the disk method. So what we're doing is we're rotating this thing around either the x or y axis so that we have a solid figure that is rotated. So if I were to rotate this f of x function around the x-axis, around this axis right here, then the solid that I would get would look something like this. So you can see how this function, if we rotate it about the x-axis, we get this solid shape. As it revolves around the x-axis, notice this line becomes a 3D shape. And any 3D shape that we have, we can find the volume for. And we can use calculus using the disk method to find the volume of this solid. Now, the idea here is very similar to what we did when we were doing cross sections. We're going to take the volumes of little teeny cylinders. And the idea is if we add all those volumes together, we will get the volume of the final solid. Now, a couple things you need to know. If they tell us that we're revolving or rotating about a horizontal axis, so if we're revolving around something like the x-axis, or we're revolving around something like the line y equals 5 or y equals -3, okay? Then if it's a horizontal axis that we're revolving around, then the equation has to be solved for y, and your a and b are going to come from the x-axis. Your a is the furthest left that your f of x function is on the x-axis, and your b is the furthest right point that your f of x function is on the x-axis. If we rotate about a vertical axis like the y-axis or something like the line x equals 2 or the line x equals -1, then we are going to solve the equation for x, and our boundaries are going to be coming from the y-axis. Whatever the highest and lowest points are on the function that we're talking about would be your boundaries or your intervals. And that idea is very similar to what we did when we did cross sections. We said that if the cross sections were perpendicular to the x-axis, we solved for y. If the cross sections were perpendicular to the y-axis, we solved for x. So very similar. That's not going to be too difficult for you to remember. So how are we going to go about finding the volume of an odd shape like this? There is no formula for a weird shape volume. We have formulas for pyramids, we have formulas for rectangular prisms, cylinders, cones, and those sorts of things. And we've talked about some of those things throughout the year. But we haven't talked about how to find the volume of really odd shapes like this. The idea is very similar to the Raman sum idea, that if we find the volume of something very, very thin and let dx represent the thickness of each portion that we're finding the volume of, then if we say the integral goes from a to b, we're accounting for every single little slice of this thing that we've divided it into. So that's what we're going to do. We're going to slice this thing up into teeny little cylinders. Now let's think about that. You know that a cylinder is like a can shape. Here's a cylinder, right? That's what a cylinder looks like. The area of its face right here would be a circle, but then if you hold it up this way, you can see you've got a cylinder. Well, what we're going to do, we're going to separate this shape into an infinite number of little cylinders like this. So if we decide to take the volume of one of those little cylinders, well, if we add up all of the volumes of these little cylinders and add them together, we've got our final volume of the entire shape. So it's like we're taking out a little slice, finding what its volume is, and then adding it together with all of these other little volumes to get our final answer. So here is the idea. This right here would be one of those little cylinders. And if you think about the volume for a cylinder, or if you just think about this as a circle. And if you think about the area of a circle, wouldn't the area be pi r squared? So as long as we could find the radius of what this shape is, then we could find the area of this circle. And if you think about the area of a circle being pi r squared, we do have to account for how thick this shape would be. We have to account for that thickness of the shape, and that thickness of the shape is said to be your dx. So if we think about the formula for the volume of a cylinder, didn't we learn in geometry that the volume of a cylinder is pi r squared times the height? So it's the area of a circle times its height for the volume of the cylinder. So the idea is, if you take the volume of all of these little teeny tiny cylinders and then add them all up from A to B, you'll have the volume of this entire shape. Now think about it. Wouldn't this little disc have a different radius than this one? Because this disc's radius is a little bit shorter than the other one. And then even smaller still, wouldn't this disc have a different radius than this one and this one? Because it's so small. But if we take the volume of this little disc with its thickness, the volume of this little disc with its thickness, and all of the ones in between, then couldn't we get the volume of this odd shape? So the idea is, if we take the integral of this function from A to B of pi r squared, the area of the circle, times the thickness of each disc, which we've learned is dx, we will have the volume of this odd shape. So now, how do we figure out what the radius is? Well, that's where your knowledge of area between two curves comes in. If this is my radius of the circle, and we know this shape has revolved around the x-axis, well then wouldn't our center of each circle be on the x-axis in this case? And so wouldn't the distance from the center to the edge of that function be considered my radius? And that's going to be the case for all of these different sized circles. My radius is going to go from the x-axis all the way up to where the function began. So I've drawn in those radius segments for each of the other circles. So to find the radius here, wouldn't I just take the function f of x minus the bottom function y equals 0? So it would be f of x minus 0, or in this case, just whatever f of x is. So if we consider the volume of this problem, it would be the integral from a to b of the function of a cylinder, pi r squared, times its height, dx. And then if my radius goes from 0 to the function, couldn't we replace r with f of x? So it's going to be the integral from a to b of pi r squared. R is going to be y equals 0. So the function f of x minus 0 would be f of x. So it's going to be pi times f of x squared times the thickness or the height of each individual cylinder, dx. So this would be my setup. My a and b would come from the x-axis, and then this is the area, or this is the volume formula for a cylinder. I think a big thing with this section is being able to visualize what it is you're finding the area of. And so I felt like this was a good way to demonstrate that. We've all seen these paper bells that you can have, and when you buy these paper bells, they're actually flat, and you have to open them up and put these little tabs in them to make them this 3D shape. So what I've done here is I've got this bell, and I'm going to say that this black line right here is a function f of x. And we're going to take this function f of x, and we're going to rotate that about the y-axis so that you can see what this bell shape would look like as one of these problems. So I'm going to take this and I'm going to copy it onto my graph. So here it is. I'm going to drag it and drop it right over here so that this bell curve rotates about the y-axis. So there it is. And now I'm going to take that and I'm going to rotate that shape about the y-axis right here. So if I rotate that shape about the y-axis, wouldn't I get a symmetrical shape on the other side of that y-axis? So that's what I'm going to do next. Okay, so there is my bell curve, and that's about as close as I can get it to being symmetrical. So I'm rotating that thing around the x-axis, and so I need to visualize what my circle might look like. So here I have drawn one of our little discs, and understand that this would be the thickness of the disc. Now this time, this one is rotating about the y-axis. So instead of having a dx, we'll have a dy because we have to get this thing solved for x. So our variable now will be y. So if this is our thickness, our radius will go from the x equals 0 line to our function there, okay? So if we're talking about the radius here, the function minus x equals 0 would just be that function. So I'm going to call this function f of y, since we have to have it in terms of y. We have to solve for x, getting our variable to be y. So our function here is f of y. So if I'm going to set this one up, notice this function goes from 0 to whatever this is. We'll call it b. So it goes from 0 to b. So it's the integral from 0 to b of pi times r, and my r will be squared, and then our thickness would be dy. And that would be the setup for finding the area, or for finding the volume of this shape as it rotates around the y-axis. So this one says find the volume of the region bounded by the graphs of y equals square root of x equals 1, and x equals 3 if the region is revolved about the x-axis. So the first thing I'm going to do is draw this. Now we know that the function y equals square root of x, we know what that shape would be. It would look something like this. So we know that a basic square root function looks something like this. It starts at 0, 0. And then I'm not even going to label this graph. I'm just going to say, so this right here is 1, and I'm going to say this is 3. So we want the region bounded by this graph, y equals square root of x, the x equals 1 line, which is a vertical line, and the x equals 3 line, which is also a vertical line. And we're going to rotate that shape about the x-axis. So if I'm trying to draw the shape that we're talking about, then I need to draw this shape symmetrical about the y-axis. So it looks like that's about this far from my axis of rotation. And this one is maybe about this far from my axis of rotation. And if I actually had a graph that was labeled, I would be able to tell exactly where those two would be. And then I'm just going to draw what I think that symmetrical thing would look like, something like that. Okay, close enough. So then I'm going to show that rotation by drawing some circular shapes on either end. And by doing that, you can kind of visualize what this thing is going to look like. So if we're talking about one of the discs in the middle of this thing, it's going to look something like this. So here is one of the little discs. I would say this, I'll draw it so that it has a little bit of thickness there. So that thickness would be my dx. Remember, my radius goes from the function down to the axis of rotation. So I've drawn my radius in red there. So if you think about what that length is, wouldn't it be this function, square root of x, minus this function, y equals 0. So square root of x minus 0 is the square root of x. So my radius is square root of x. So the setup for this one would be the integral from my a to b. And remember, in this case, my a is 1. My b was 3. So the integral from 1 to 3 of the cylinders formed. So this cylinder, this little cylinder would be pi r squared. So pi times the radius squared. Remember, the radius we said was square root of x, but we have to square the radius. And then that's times the thickness dx. So here's our setup. If we simplify that, now before we integrate, we can always take the pi out. Remember, pi is a constant, so it can come out to the front. The square root of x squared is just x. So this one ends up being a very, very simple problem. We could integrate that. The integration would be x squared over 2, and then plug in the 3 and the 1 and come up with our answer. And so if I do this one on my calculator, my answer is 4 pi. Okay, so now that you know the basic setup of these, we're just going to do a few examples, and I'm going to have the computer generated pictures over here. I found these online. It'll just save us a lot of time. So this says find the volume of the figure bounded by the graph of y equals x equals 0, and x equals 4, rotated about the x-axis. All right, so y equals x, remember that is the identity line, and we're rotating that line from x equals 0 to x equals 4 about that x-axis. And you can see here that the shape we're going to get is a cone. Okay, so we have a volume formula for a cone. We could take the volume formula for the cone, find that answer, and then compare it to the integration formula that we'll get. It should be the same answer. So that kind of proves that this would work, but we're not going to do that for the sake of time. We're just going to set this one up using the disk method. So we know that the radius here is going to be the difference between the function and the axis of rotation. Here the axis of rotation is y equals 0. So the function x minus 0 would just give us a radius of x. So radius is x. And so if we're going to set this one up, we know the integral goes from 0 to 4. It's pi r squared. I'm going to put the pi on the outside. Our radius was x. We square the radius because it's pi r squared. And then the thickness is dx. When we integrate this, we will get our answer. And so my answer when I did this on my calculator is 64 pi over 3. Okay, this one's very similar to the last one that we did. We're using the same function, but this time it's going from 0 to 4, but the axis of rotation is the line y equals 1. So I want to make sure you understand that it doesn't always have to revolve around one of the axes. It could revolve around any horizontal or vertical line. So if it revolves around something other than the axis, we have to understand how to get the radius. And so here is this function. This is the y equals x line. Here is our axis of rotation this time. So we're going to rotate this about that y equals -1 line. So that's what we're rotating about. So when I do that, I'm going to get a picture similar to the last one, but it will look a little bit different. So here's what we get when we rotate this figure about that y equals -1 line. Notice we still have something that's shaped like a cone, but it looks like the edge of the cone has been sliced off, because remember, if it kept going, the cone shape would be right here. But they wanted us to cut it off from 0 to 4. So now our shape looks like a cone that has its point cut off. So that's what this is going to be. So my radius now has to go from the function y equals x down to the -1 line. And remember, to get this length right here, we have to subtract the top function minus the bottom function. Well, the top function here is x. The bottom function here is -1. So our radius is going to equal the top function minus -1, or x plus 1. So now that we know the radius, we can set up the volume formula. So the volume of this will be equal to the integral from 0 to 4 again of pi r squared times the thickness, or h, dx. And remember, since this one is rotating about a horizontal line, we do need it solved for y, so it was already solved for us. Again, I could take that pi to the outside since it's a constant before I integrate. I'm going to save time by integrating on my calculator. And so when I put that in my calculator, I get the volume to be 124 pi over 3. The next example says rotate the region formed by the lines y equals x squared, x equals 2, and x equals 5 about the x-axis. So that's a simple parent function for a parabola, y equals x squared. We're going to rotate that function about the x-axis, giving us this little funnel shape right here. And if it's going from x equals 2 to x equals 5, those would be our boundaries. So the setup for this one, if we think about what the radius would be, our radius is going from the function down to the axis of rotation. So that would be the function x squared minus 0, or just x squared. So if I set up this integration, it would be the integral going from 2 to 5 of pi r squared. I'm going to put the pi on the outside. And here, since the radius is x squared, we're going to square that, which would give us x to the 4th, times our thickness dx. And again, for the sake of time, I'm going to put that in my calculator. And my answer in this case is 3093 pi over 5. We also need to be familiar with what if this thing revolves around a vertical axis. So it's the same thing. We will draw the function, and this is the same function, y equals x squared. It says find the volume of the figure bounded by the lines y equals x squared, y equals 16, so that would be this line right here, and y equals 1, this line right here. And we're going to rotate that about the y-axis. So if we rotate that function about this axis, this is the shape that we're going to get. It looks like kind of a cereal bowl. And if we're talking about the individual little discs in there, try to draw one real quick. I'm talking about that little disc right in here. So if we're talking about the radius of that disc, aren't we talking about that black line right there? So the radius here would be the difference from the function that's to the right minus the function of rotation. This is rotating about the y-axis. So we do have to solve this thing for x. So we have to get x by itself. So if my function is y equals x squared, then to solve this thing for x, wouldn't I need to take the square root of both sides? So my radius would be the square root of y minus 0. So my radius would be the square root of y. So if I do my setup, my integral goes from, now a this time is 1 and b is 16, because remember they have to be on the axis of rotation. So that would be my a and b, 1 and 16. I put my pi on the outside because my volume is equal to pi times the integral from a to b of my function squared, or of pi r squared. And here r is square root of y. So if I square the square root of y, I'm going to have a y here. And then my h will be my thickness dy. And again, to save time, I'm going to integrate on the calculator. And that gives me a volume of 128 pi. So here's an example I took from Delta Math. A lot of times they're going to draw the picture for you, so it makes it a little bit easier on you. Let the region R be the area enclosed by the function f of x equals x cubed plus 1. The horizontal line y equals 9 and the y-axis. Find the volume of the solid generated when the region R is revolved about the line y equals 9. You may use a calculator and round to the nearest 1,000. Okay, so we are rotating this thing about the y equals 9 line there. So we're rotating about this axis. So if we think about that, let's see, we need to draw this shape symmetrical to the y equals 9 line up here and see what our region is going to look like. So let's see, it looks like this crosses at 0, 1, and that would be 8 spaces from the axis of rotation. So I'm going to go 8 spaces up right here, and it looks like this is 7 spaces from my axis of rotation. So I'm going to go up 7 again. And again, the reason I'm doing this is just so that I could get a good estimate of what my real shape is going to look like. And so if I just draw that line, it's going to look something like that. It's revolving around a horizontal line. So we know we're going to need this function solved for y. So we know our function here is y equals x cubed plus 1. And it's already solved for y, so we're good there. We know that when we do this, our a and b comes from the x-axis because it's rotating about something that's horizontal. So my a and b, it's going to start at 0, and then it looks like it ends here at 2. So our a and b goes from 0 to 2. So my integral is going to go from 0 to 2. So my volume will be equal to pi of the integral from 0 to 2 r squared. Now we have to figure out what r is. Well, you have to visualize what one of your little discs would look like. So I'm going to start here, and I'm just going to try to draw a little disc that would represent one of these little circles that we're finding the area of. And then remember, when we tack the dx on, that is actually finding the volume of a cylinder. So this is a good idea of what one of the circles would look. So then we need to know what the radius is. Now my radius has to go from my original function to my axis. Now I could see somebody trying to draw it from here to here, but remember, this function we drew in. This is just kind of the mirror image of what the real function was. So don't we have to take, for my radius, we have to figure out what this length right here is. This would be my radius. So to get that radius, don't we take the top function, which would be y equals 9, minus the bottom function, which is the x cubed plus 1. So my radius is going to be equal to 9 minus that function that they gave us, x cubed plus 1. So this is my radius. So if I distribute that minus sign, I'm going to have 9 minus x cubed minus 1, which is 8 minus x cubed. So this is my radius. That's what I would put up here in my function. Remember, it's pi times radius squared, so this needs to be squared. And then we have to multiply by the thickness, dx. And this would be my setup. Now your directions say to round to the nearest 1,000th. So I'm going to save time by putting that in my calculator. And my calculator gives me 576 pi over 7. If they ask for it in thousandths, I could convert that and say that that is 258.508. So if you round to the nearest thousandth, this is what it would be. I typically prefer the exact answer, and no rounding is required if you have the exact answer, but it's going to depend on what the directions ask for. So just follow the directions in the individual problems, and you should be fine. So I hope this gives you a good idea of what the disk method is. To continue with this, what's going to happen in the next lesson is we may have two functions that are rotating around an axis at the same time, and when that happens, it forms a hole in the middle of our disk, making it a washer. And so we have to learn how to account for the hole in that volume.